Hey, grade 10 learners, welcome to another explainer. You know, if you've ever stared at a math test and just felt this immediate wave of panic when asked to classify some messy, complicated-looking number, well, you are in exactly the right place. Today, we're taking a little journey into the real number universe, and my goal for this explainer is super simple. I want to give you a foolproof, incredibly clear mental decision tree. By the end of this, you're going to be able to instantly classify absolutely any number they throw at you in your curriculum. You'll be looking at these numbers not as weird, confusing symbols, but kind of like old friends.
So here's our quick roadmap for how we're going to conquer this together. First up, the real number universe. Second, the rational number club. Third, the irrational rebels. Fourth, the square root trap. And finally, the ultimate classification test.
All right, section 1, the real number universe. Okay, let's dive right into this.
So let's define this vast mathematical universe we're exploring today. When we talk about real numbers, we aren't talking about numbers that actually exist versus, imaginary ones. Actually, scratch that. In higher math, there literally are imaginary numbers. But for grade 10, the real number system, that is your entire mathematical playground. And this huge overarching group is split into two very distinct rival camps. We're talking two groups with entirely opposite traits. On one side, you've got the strict rule followers, and on the other, the rule breakers. Let's meet the first group.
Section 2, the rational number club.
Welcome to what I like to call the fraction faction. These are the highly predictable, rule-following rational numbers. So, what does it actually take to get past the bouncer and into this club? The one absolutely crucial requirement is simply the ability to be written as a fraction. If you can formate a number as a over b, where both a and b are neat, clean integers, and b isn't 0, obviously, you are in. It is all about predictability. If a number's decimal form terminates, meaning it just neatly ends like 0.25 or 0.6, it's easily written as a fraction, so boom, it's rational.
But this raises a really interesting question. What about standard, everyday numbers? Think about the number 8, or 0, or even -5. How does a standard whole number fit into a club that is supposedly exclusively meant for fractions?
Well, here's the secret. Whole numbers are actually just fractions in the perfect disguise. Literally, the number 8 can easily be written as 8 over 1. -5? That's just -5 over 1. Even 0 is just 0 over 1. By simply putting these integers over the number 1, they completely validate their membership in the rational club. They follow that A over B rule flawlessly.
Okay, but let's look at something just a little more suspicious. What about a number like 0.333, where those three little dots mean the threes go on forever? It never terminates. It literally never ends. Does a never-ending number get kicked out of the rational club? Not at all. Because even though it never ends, it repeats in a perfectly predictable pattern, and because it has that repeating pattern, it can be perfectly formatted as the fraction 1 over 3. The exact same thing goes for a number like 2.181818, which is really just 24 over 11. As long as there is a repeating pattern, the number can be expressed as a fraction, completely proving its rational identity. Moving on to section 3, the irrational rebels.
All right, let's leave the neat, orderly fraction faction behind and transition over to the chaotic side of our universe, the irrational rebels. These are the numbers that stubbornly outright refuse to follow the fraction rule. The core takeaway here is that an irrational number cannot, under any circumstances whatsoever, be written as a simple fraction of two integers. There's no a over b here, folks. When you look at their decimal forms, you're going to see two core traits. They never ever end, and they never ever repeat. They are completely wild, infinitely long, and just entirely unpredictable.
Now, the most famous irrational rebel in the history of mathematics is, of course, pi. We usually just round it to 3.14 to make our lives easier in geometry class, right? But in reality, pi is approximately 3.14159.265, and it just keeps going. Forever. I mean, supercomputers have calculated millions and billions of digits, and it never terminates, and it never falls into a repeating pattern. It is the ultimate irrational number.
And there's another really famous mathematical constant you'll run into as you get further into high school math. It's called E, or Euler's number. Just like pi, E is approximately 2.718281, and it stretches on into infinity without ever repeating a sequence. Because you can never pin down exactly where these decimals end or loop, you literally can't turn them into a neat little fraction. They are proudly, stubbornly irrational.
Section 4, the square root trap.
So, let's see how all this builds into what I call the square root trap. Listen up, because as a grade 10 learner, this is honestly the biggest trap you will face on math tests.
It is just so easy to assume that every single square root symbol you see automatically means the number is some messy, irrational rebel. So I want to test your intuition here. Is the square root of 25 rational or irrational? Does that radical symbol mean it's a rebel, or is it secretly a rule follower? Think about it for a quick second. If you said rational, you absolutely nailed it. See, because 25 is a perfect square, the square root of 25 elegantly simplifies down to the whole number 5. And as we figured out earlier, 5 is just 5 over 1, a perfect rule-following rational fraction. The same applies to the square root of 16, which is just 4, or the square root of 36, which is 6. Do not let that square root symbol trick you. If there's a perfect square hiding inside, the number is for sure rational.
Now let's contrast this immediately with non-perfect squares. Numbers like 2, 3, 5, 7, or 10. If you punch the square root of 2 into your calculator, you are not going to get a clean whole number. You are going to get a messy, never-ending, non-repeating decimal. These non-perfect squares, they are the true irrational square roots.
Which brings us to Section 5, the ultimate classification test.
Okay, we've covered the rules, we've spotted the clever disguises, and we've avoided the traps. Now, what's really interesting about this slide is how beautifully this table maps out literally every scenario you're going to face on a test. Let's rapid fire through this. The number 5, rational, because it's 5 over 1. -7 over 9, rational, it's already a fraction. 0.6, rational, because it neatly terminates. 0.1212 repeating, rational, because that pattern makes it super predictable. The square root of 16, well, it's a perfect square, making it 4, so it's rational. But then, we hit the square root of 2, a non-perfect square, making it irrational. And finally, pi, the absolute king of the non-terminating, non-repeating decimals, making it strictly irrational.
Let's directly juxtapose our two rival families right here to visually lock in these big picture differences. Over on the left, rational numbers. They can always be written as a over b. Their decimals are polite. They either terminate and end completely, or they repeat in a totally reliable pattern. On the right, the irrational numbers. They completely reject that a over b format. Their decimals are just pure chaos. They never terminate and they never ever repeat.
So, to make sure you never miss a question on this topic again, I want to give you this perfect study guide checklist. Write this down. If a decimal ends or repeats, it is rational. If a decimal never ends and never repeats, it's irrational. If you're looking at a square root, check if it's a perfect square. If it is, like 9 or 25, it is rational. If it's a non-perfect square, like 7 or 10, it is definitely irrational. Keeping these 4 simple rules in your head guarantees success when classifying these numbers.
And that brings us to the end of our little journey through the real number universe. So, what does this all mean for you? Well, next time you encounter a chaotic, never-ending number, or some sneaky square root trying to trick you on a test, will you know how to uncover its true identity? Armed with your brand new mental decision tree, I know you will. You've got the tools now to look right past those complicated decimals and radical symbols and confidently sort the rule followers from the rebels. Keep practicing, trust your checklist, and I'll see you in the next explainer.